Hello, welcome to lesson 6.2. We're going to talk about constructing a confidence interval and do it for proportions. So there are a couple of learning objectives here. We want to talk about the procedure for coming up with a confidence interval. We need to talk about the conditions and how to verify them. We want to define something called the margin of error, which you may have heard about or seen before. Then we're going to be able to calculate what this confidence interval is and use that to estimate based on the proportion. So we're going to go ahead and jump on into the essential knowledge. There's a lot here. There's like 3 slides of this, so I'm not going to jump into it too deeply, but you can read this. You definitely want to read through these slides. You want to, and maybe come back after we do an example or two. But what we're going to do is try to define a confidence interval for a sample proportion, or we're going to find a proportion of something. So we're going to measure it and end up with a percentage or a decimal, or we're going to be doing with decimals. And we're going to be figuring out a category, how many of what percentage or what proportion of a categorical variable has a certain trait. Okay. And that's what we're going to try to do. And we see this a lot when we're talking about the percentage of people who are going to vote, especially if you're into politics. They talk about certain percentage of people are going to vote for a measure and a certain percentage vote against it. And that's kind of the idea of a confidence interval. Okay. There's a formula for that, and we are going to have to be aware. There's a standard, what they call standard error here. We're going to take the p hat that we measure when we survey or gather our data. So we have the success times the failure rate, 1 minus what we're looking for, divided by the number that we sample, divided by the square root. That's going to give us our error. And it's sometimes also called the margin of error. It's how far off we could be. And then we're looking for, well, I guess actually the margin of error is here when we talk about the z-score, and we're going to be talking about that in a little bit, about how many standard deviations. Remember, a z-score is how many standard deviations we are from the mean, and so we're going to use that to find those intervals, and the 68, 95, 99.7 rule is going to come back into play again. And so when we do want to talk about, then all of these formulas are will be available to you. We're going to take the actual number plus or minus the margin of error. So, and when you'll see this on, again, since it's always I'm into politics, and some of you might be as well, they might say 53% of people believe a certain thing, plus or minus a certain percentage. So if they say 53% are in favor of a measure, some initiative, with a margin of error plus or minus 4%, it means it could be 4% higher or 4% lower. So it could be as low as 49 or as high as 57. We do want to be careful about the statement, the conditions, and we'll talk about some of that later on too. Okay, so what does a confidence interval really mean? Is it's a range of values that is likely to include or likely to capture the true percentage. We don't actually know how many people are in favor of a certain, will vote for a certain measure. So, suppose we have an initiative on the ballot. We don't know the actual percentage of people will vote until after the fact. When they survey, they're getting close. And then they have the margin of error, and they're hoping that their margin of error captures the true meaning of the true number. And that'll happen depending on how wide you want it to be. The more confident you want to be, the bigger you're going to have your spread. So 95% confidence is a good number that allows us to go almost. And when we say the 68, 99.9 whatever rule, we use 95 for 2 standard deviations, but it was really a little bit more than 95. It's actually 1.096 is exactly 95. So if we go negative 1.96 standard deviations below the mean and 1.96 standard deviations above the mean, we will capture exactly 95%. So we're going to use 1.96 and negative 1.96. So here's what we're doing. Here's the idea. We are looking at in this problem, we have a firm that's estimated, I'm gonna have to move my face, sorry, I'm in the way, not the first time, to find the percentage of adults in a city that have cell phones. So they're gonna survey 500 people and ask them whether they have cell phones. Of the 500 people surveyed, 421 said yes, they own cell phones, and whatever. We're not going to actually say whether this is true or not. So they survey 500 people and get 492 responses. So this is the sample. Hold on a second. That's how many they sampled, and this is how many yeses they got. So that means they got 79 no's. Okay, and that's fine. What they want to do is, so that would be what we would end up with is a percentage. They've got about 84% or 84.2%, I think, of people is what they would estimate. Now, that may not be the exact for the whole city. It may be only those people they surveyed. They may not have surveyed a wealthy area, or maybe they surveyed, didn't just evenly distribute it. So they need to be a little bit more wide than saying, oh yeah, it's 84%. It's not exactly 84%. So it could be higher, it could be lower. So what we're going to do is we're going to write up an argument for this. This is what a statistician does. The first thing they do is we have to say that we did it randomly. Okay. And the problem, and where you're going to be looking for this in the condition, the problem did say randomly selected adults. Now, I don't know how they did that. I don't know whether it's actually valid or not, but all I do know is the problem says it, so I have to say it back. When you're writing one of these up, you have to check, first part, you have to check your conditions, and one of them is, of course, random. The next thing is independence. So it's random and independent. And independence in our case is that they sampled less than 10%. If they sample more than 10%, then they lose independence and they end up starting to overlap some traits. So what we're going to say, we need to say, and we don't know this for a fact, but we're assuming a large city has more than 5,000 people in it. Hot Springs has over 30,000 people, and Hot Springs is not considered a large city. So whether it's not, or you as the author of a stats paper need to say that for us in the AP. Okay. So the first thing you got to do is tell us that, identify that they're random and that it was less than 10%. Then we want to check for normal. And this is where we get the p hat and we multiply it by the number that they surveyed, and it has to be bigger than 10. And so that's the successes have to be bigger than 10. It has to be bigger than 10. And then the failure is the complement. The failures also have to be bigger than 10. So you have to show me that the number, they're going to get enough in each category. Okay. So yes, you need to write this down. I don't care if it seems redundant. You're going to do this every time. You're going to check for independence, and then you're going to check for normal. All right. That's your conditions. You have to check the independence and normal. After you've done that, then you can go on and just tell me what you're about to do. You're going to compute a one sample Z interval. We're going to use Z for Z scores on a proportion. So we're going to compute a confidence interval on a proportion. And you're going to take the p hat that we got, which was achieved by taking 421 divided by 500. And you're going to take the Z score that we want for, now where does this come from, this 1.96? This comes from using the 95%, okay? You're gonna need to know some basic ones. 95% is 1.96, and that comes from the Z-score chart, okay? But we're gonna use 95 a lot, so you probably need to just memorize 1.96. Okay, so now we're going to be able, we have the p hat, we have the z star, we have n is 500. We can go ahead and plug all those numbers in. So we're going to plug in, and you basically what I would do here is 0.842 plus or minus 1.96 square root of 0.842 times 1 minus 0.842 all over 500. And I'm sorry, my handwriting is crummy, but you could plug those numbers in and do the calculations. Some of you need to get a power cord apparently, but do it, get your cord. And so we plug all that in and we would get our numbers here. So we would get, when we do, remember plus or minus means two different things. So on the low end, when we compute it, we're going to get 0.81. And then on the high end, we're going to get 0.87. So what does that tell me? All right. The true measure, I have a 95% chance of capturing the true measure between those two numbers. Okay. I mean, it could be outside of that range. 5% of the time, it would be outside of that range, but I have a 95% chance of capturing the true value. So the true population proportion that has a cell phone is somewhere between 81% and 87.4% with 95% confidence. And that's what you would end up writing. So we estimate with 95% confidence that blah, blah, blah. And I basically said it before I wrote it. Okay. So you have to write all this up. This is how, I mean, you're not going to be doing a ton of these, but when you have an open response question, you need to do part one, you're checking for normal and independence. Part two, you're going to name your test and tell me what you're doing. You show me your variables. You got to tell me that you identify all the variables. And then part three, you're going to do the calculation and interpret it at part four. You have to write that concluding statement. Okay. And guess what? This needs to be in context. Okay, you need to spit back that we're talking about what the problem's about. If you tell me the confidence interval and you don't mention that this is about cell phones, you're going to lose. Okay. And it's not like, it's like we've been doing all along. You just are going to give back what you were given. Okay. All right, let's look at, oops, sorry, went slide too far. So that's your confidence. I mean, and that's the way we would summarize it. We are 95% confidence interval would contain the true value. We have 95% confidence that would actually contain the true value. So we could be wrong. Statisticians will never tell you they're 100% correct, because to be 100%, we'd have to go for a negative infinity to infinity. But they can increase, if you want more confidence, you're going to have to widen your range. Okay. So if we said, if we wanted to be 99.7, we'd have to go like the 3 standard deviations. But if our confidence interval is too wide, it's not too helpful. I'm pretty comfortable with 81 to 87. That's not a huge range of values. But when we start talking about, if we want to be 99.9999 confidence, you're going to be saying like, oh, there's between 0 and 100% confident, or 100%, 0 and 100% people who have cell phones. Well, that doesn't tell you anything. You need, okay, so if you want more confidence, you're going to have a wider range. If you have a narrower range, you'll have less confidence, which makes sense. Okay. All right, so the numbers that you need are on this slide. Yeah, and these are the most common ones that we see. If you want 90% here, when the problem says 90%, I should probably write these down too. It's 1.645. When you want 95%, you're going to use 1.96. And if the problem asks you to do a 99% confident interval, you do 2.576. You want to write these down somewhere. I mean, you can look these up in the chart because they're right here. It is there. Here it is there, and here it is there in the in the Z-score chart. And those are the 3 that will come up most often. You'll never, I mean, I'm not going to say you're never going to get anything different, but most of the time you're going to get 90, 95, or 99% confidence intervals. And that's a Z-score. That's that Z-star score that we're going to use in the formula. That's implied by the problem. All right, so let's try another one. Okay, so now we're talking about a class project, it's political science, because again, I'm into that kind of stuff a little bit too. So we have a student, political science student at a large university wants to estimate the percentage of students who are registered voters. He surveys 500 students and finds that 300 are registered voters. So we want to compute a 90% confidence interval. So a couple things we're going to look at. 90% right here. That's going to tell me Z star was 1.645. We're looking for this word. I see it, makes me happy. All right. And he surveyed, this is my number that he surveyed. And because it's a large universities, like Fayetteville's 20,000 kids or something like that. I mean, I even went to a small liberal arts school right here, Marietta College in southeastern Ohio, and it was 2,000. Now my college was a small college, but it still had over 2,000 students in it. Okay, we don't know how many students is, but we are going to assume that. And so what you're going to do the same thing, the same write-up. So I'm going to go a little faster this time. First thing we're going to do is check for independence. The 500 were randomly selected. I found that word. You want to find random in the problem. And you want to say that it's less than 10%. So independence means it's got to be random and less than 10%. Okay. You want to then check for normal. That means 10 successes, 10 failures, at least 10 successes and 10 failures. So we had 300 successes, which meant he had 200 failures. Both of those are bigger than 10. You have to do this every time. Okay. Then we're about to name the test. Again, this is going to be the same format for a whole semester pretty much, so get used to it. You're going to name a one sample Z interval. Now this will change. Later on we'll have other tests and other confidence intervals. We might be doing it. We're going to be doing this for means. Right now we're just doing it for proportions. Later we'll be doing it for measurements. Okay, so we're going to do a one sample Z interval for a proportion. Our p hat was 0.6, which was the 300 divided by the 500. The Z star, remember I said it was 90% confident, I had that earlier. And the number, I have to identify all of the variables in this formula. You don't have to write this formula down, that's because it's going to be on your formula sheet. It doesn't hurt to have it there, but you need to have all of the formulas in all the values defined in that formula. Okay. So now we're ready to do some calculations. So we'll calculate the values. We're going to find on the low end 0.564 and on the high end 0.363. I'm sorry, 636. If you're using a calculator to do this, you can type it all in with the minus and then go back and grab it again, like do second enter or go arrow up and highlight it, press enter and change that plus to or that minus to a plus. So you can do these as two different. Don't type it in. Just make sure you get it in right with the minus the first time, and then do it again with this plus. So that gives me 0.564 to 0.636. I'm going to say it's right this time, and then we have to interpret it. So with 90% confidence, we can say that the true percentage of all students who are registered to vote, there's my context, right? Registered to vote. Students registered to vote. And just spit back the exact wording from the problem. Don't try to ad lib here. That 90% confidence, the true percentage of registered voters and the students among the students is between 56.4% and 63.6%. And now notice that's a wider range, okay? Because first of all, we sampled fewer people in this one, I believe. Yeah, I think we did. And we had a wider, or we had 90%, so we could spread out a little more, okay? Okay, so let's take a look at the interpretation. Okay, so 90% confidence that the structure will contain the true proportion of students who are registered voters. Okay. So Anyway, let's move on. Now, the next thing, remember, I think I told you once earlier that at one point you'd have to do some algebra, and this is it. This is where you might have to do some, the only time you actually need to do some mathy algebra. So if a company wants to have a certain degree of accuracy, remember I told you, yeah, we can have confidence intervals that are very wide, but when we have a very wide confidence interval, it doesn't be very helpful. So we want to know, the way we can control it is by changing the Z star. We can change the width of the interval, or we can survey more people. And what we're going to be doing is focusing on solving for this number n. How many do I need to get this part right here at a certain number? I want this number to be 0.03. Okay, if I can make that range 0.03, then I can be good to go. Okay, and we know we're dealing with 90% confidence. Okay, so we're looking at 90% confidence. So I know I'm going to have 1.645 in there, and I know, let's see here, with a p-hat of 0.5, right? And notice Miss Young has been using this when she wrote this. That's just because it's a pain in the neck. You want to write this, okay? So it's just be careful with that. Okay, so what we're going to do is we're going to take that, and we know that the Z star score is 1.645, and she tells you to use 0.5 for p-hat, which means 1 minus p-hat is 0.5. And so we want to solve that for 0.03 for solving that by n. So what I'm going to do is divide by the 1.645, and that gives me the 0.0182, and you're going to get some algebra there. I got to square both sides because all of that I have a square root to get rid of. So when I square both sides, I have 0.25 over n equals 0.018, yada yada squared. And then to solve that, I'm going to take 0.25 and divide it by the squared and all that little cross multiplication action, because what you're going to have is, let me scoot over here and draw it out for you. What you're going to have here is 0.25 over n equals 0.18 blah, 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 squared over 1. So when we do a little cross multiplication, we'll get n times 0.18, blah, 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 squared equals 0.25. And then we're going to divide by 0.18 squared. And that's going to give me n. All right. So that's how she got that, just if you didn't catch the algebra. All right. And computing that says they need to survey a 751.7. Now, when you answer the question for this, you're gonna have to go up because they want to make it be within 0.03. So what if we did 751? That would be a little bit, too big. So we have to go up. You're always going to jump it up. So even if that was 751.01, you're still going to round it up to 752. So they're going to have to go to 752. Okay. So they got to go up no matter what. You're always going to bump up the n. All right. All right. And that's 6.2. I hope you're having a great day.